Hello everyone, and welcome to the Introduction to Logistic Regression lecture. In this lecture, we'll discuss classification problems, how to use logistic regression to solve them, and how to interpret the results of a logistic regression through a confusion matrix. If you want to understand the full mathematics behind logistic regression, go ahead and read sections 4 through 4.3 of Introduction to Statistical Learning by Gareth James. Moving along, we want to learn about logistic regression as a method for classification. In machine learning and statistics, classification is the problem of identifying to which of a set of categories a new observation belongs to, based off of training data. Some examples of classification problems include trying to detect spam versus ham emails, trying to detect whether someone's going to default on their loan or not, or even trying to diagnose a disease. For example, trying to tell if someone has cancer or not. These above examples are all examples of a binary classification, meaning we have two classes. So far in our studies, we've only seen regression problems where we try to predict a continuous value, such as the price of a house. Although the name may be confusing at first, logistic regression allows us to solve classification problems where we're trying to predict discrete categories. The convention for binary classification is to have two classes, 0 and 1. However, we can't use a normal linear regression model on a binary group. It won't lead to a good fit. For example, if we take a look at this plot below, we have a y-axis which represents the probability of belonging to a particular group. Let's go ahead and imagine that this example plot is trying to predict likelihood of paying back a loan. We'll go ahead and label 0% probability as defaulting on their loan, meaning they have a 0% probability of being able to pay back their loan. And at the top, we have 1 or 100% probability as fully paying back their loan. We'll go ahead and mark the x-axis as some sort of paycheck value. That means if we go ahead and look at this data, as your paycheck goes lower, you have a closer to 0% probability that you're going to be able to pay back your loan. As your paycheck value gets higher, you then have closer to 100% probability of paying back your loan. The reason these yellow dashes are all either on 0% or 100% is because this is training data. Now, if this was training data and we try to use a linear regression model on it, we would get a very bad fit. We would actually end up predicting probabilities below 0%, which doesn't really make any sense. Instead, we can transform our linear regression to a logistic regression curve. And you'll notice our logistic regression curve can only go between 0 and 1. And that's going to be the key to understanding classification using a logistic regression curve. The sigmoid, also known as logistic function, is going to be the key to understanding using logistic regression to perform a classification. The key secret to this function is that it can take in any value and its output is going to be between 0 and 1. If we take a look at the equation here on this plot, we have the sigmoid function plotted out. On the z-axis is going to be the bottom line, usually the x-axis there, but here we're denoting it as theta of z. And the formula is theta of z, so the function of z, is equal to 1 over 1 plus e to the power of negative z. The key thing to notice here is that it doesn't matter what value of z you put into the logistic function or the sigmoid function, you'll always get a value between 0 and 1. So again, if you take a look at this plot, it doesn't matter that whatever value you put in for z, the output along the vertical axis is always going to be between 0 and 1. And that's the key to the sigmoid function. This means that we can take our linear regression solution and place it into this sigmoid function. And that's going to look like this. Remember, our linear model followed a basic y equals mx plus b principle. Here we have our linear model as y equals beta naught plus beta 1 times x. If we take that linear model and put it into the sigmoid function, we finally are able to transform this linear regression to a logistic model, meaning it doesn't matter whatever the value of the linear model output actually is, it's always going to be between 0 and 1 when we place it into the logistic model or the sigmoid function. Again, if you want more review on this mathematics, make sure to read sections 4 through 4.3 of Introduction to Statistical Learning. But the basic premise of all of this is that this results in a probability from 0 to 1 of belonging in the 1 class. Again, doesn't matter what we put in on this horizontal axis, on the vertical axis, we'll always get some sort of probability between 0 and 1. That means we can set a cutoff point, usually at 0.5, and we'll say if anything below results in 0.5 or below 0.5, that will go to class 0. Anything above belongs to class 1. So we're going to transform that 0.5 probability as a cutoff point. Let's go ahead and do a quick recap overview of what we just discussed. We can use the logistic function to output a value ranging from 0 to 1. Again, it doesn't matter what we put along the horizontal axis, we get a value from 0 to 1. Based off of this probability, we will assign a class by putting a cutoff point at 0.5, which makes sense because we want to say if the probability is 50% or less of belonging to class 1, then we should classify this as class 0 in our binary classification. If we have a probability of 0.5 or above of belonging to class 1, we'll go ahead and assign this new point to class 1. Alright, so let's go ahead and talk about model evaluation and using a confusion matrix. After you train a logistic regression model to classify some training data, you're going to want to evaluate your model's performance on some test data. You can use a confusion matrix to evaluate classification models. A confusion matrix is a table that is often used to describe the performance of a classification model on a set of test data, for which the true values are already known. The confusion matrix itself is actually relatively simple to understand, but sometimes the related terminology can be confusing. Let's go ahead and walk through this example. In this case, we have a binary classification problem. So in this example, we're testing for the presence of a disease, where no is a negative test, which is false equals 0. Yes is a positive test, where true is equal to 1. What can we learn from this matrix? Well, there are two possible predicted classes, yes and no. If we were predicting the presence of a disease, for example, yes would mean that they have the disease, no would mean that they don't have the disease. The classifier made a total of 165 predictions, meaning 165 patients were tested for the presence of the disease. Out of those 165 cases, the classifier predicted yes 110 times and no 55 times. In reality, meaning we already have labeled test data, 105 patients in the sample have the disease and 60 patients do not. Now let's go ahead and define the most basic terms. The basic terms are the whole number terms, so not rates, just whole numbers. And those terms are true positives, true negatives, false positives, and false negatives. You may already be familiar with this terminology if you've ever had to deal with studies related to vaccine checks or disease checks. A true positive are the cases in which we predicted yes, that they have the disease, and in reality they do have the disease. That's TP, true positive. In this case, you can find it here at the bottom quadrant where TP is equal to 100. True negatives are where we predicted no, that they don't have the disease, and in reality, again, they don't actually have the disease. That's on the upper left-hand corner, TN, and that's equal to 50. So those are true positives and true negatives. Then we have false positives and false negatives. False positives are where we predicted yes, that they have the disease, but in reality, they don't actually have the disease. This is also known as a type 1 error. Then we have false negatives, where we predicted no, they do not have the disease, but in reality, they actually did have the disease. That's known as a type 2 error. Then we can talk about rates. The first rate we can discuss is accuracy. What this is actually getting at is overall, how often is it correct? A lot of times when you hear reports on studies, they'll just tell you the accuracy. And the accuracy is calculated by the number of true positives plus the number of true negatives over the total. In this case, our model is 91% accurate. Then we have the mixed classification rate, which is answering the question, overall, how often is the model wrong? This is going to be calculated by the number of false positives plus the number of false negatives divided by the total. So that's 15 divided by 165. Overall, this is 9% error rate or misclassification rate. Now let me discuss a nice quick way to remember false positives versus false negatives, or your type 1 error versus your type 2 error. Remember, our false positives that I'm pointing at here with the laser, FP is equal to 10, that's where we predicted yes, but they didn't actually have the disease. That's type 1 error. False negatives is where we predicted no, but they actually do have the disease. That's known as type 2 error. If we go ahead and move along, we can think of type 1 error and type 2 errors as this funny little diagram as a nice way to remember it. So a type 1 error is where you're telling a man they're pregnant. Again, you're predicting yes, they're pregnant, but they actually don't have the pregnancy. A type 2 error is a false negative. Here you're saying someone that's obviously pregnant that they're not pregnant. So you're predicting no, but they actually are pregnant. And that's the difference between a type 1 error and a type 2 error. False positives versus false negatives. In statistics, they're commonly referred to as type 1 or type 2 instead of their actual names, false positive or false negative. Hopefully, this is a nice, helpful, and funny reminder on how to actually memorize these terms. Let's go ahead and begin to explore an example of logistic regression using the famous Titanic data set. We'll use Python to attempt to predict whether or not a passenger survived based off of their features. Then, you'll have a portfolio project with some advertising data, trying to predict whether or not a customer clicked on an ad. Okay, thanks everyone, and I'll see you at the next lecture.